Okay, so up till now, we've kind of assumed that most chemical reactions are what we would call completion reactions, right? What's a completion reaction? It's a reaction in which one or all of the reactants are used up and the reaction stops. Think of like a limiting reactant situation that you may have learned about in the past, right? You have a certain amount of reactant and the concentration, here's your rate. That looks like a nice first order or maybe second order kinetics, right? So the reactant concentration is going to go down and then the product concentration is going to go up. But as soon as the reactant runs out, there's no more product to be made and we say the reaction stops, okay? So that's what a completion reaction is. But as we learned the other day, many reactions are reversible. And the definition of a reversible reaction is, I think I even mentioned it the other day, it's a reaction in which the products can reform, not reform like you're going to be reformed, right? But re-become the original reactants, right? And so we saw that with the copper sulfate and NaCl and water reaction. So how do we write the reversible reaction? Well, if it's a completion reaction, you would say, well, reactant becomes product if it's a completion reaction, right? Because that's what happens, and it doesn't go backward. However, what about a reversible reaction? Well, the reactant can become product, and we call that the forward direction. But then we just said the product can re-become the original reactant. And we call that the reverse direction or the reverse reaction. And rather than write it, oh, reactant can become product and then product can become reactant, we write it, reactant becomes product, and we use a double arrow. So the double arrow, and so when you have this terminology or this how we designate this here, the left to right is what we would call the forward reaction, and right to left would what we would call the reverse reaction. Now let's think about this. We could actually write this the other way, right? We could write this the other way, and it would still be reversible, right? And we would call this the forward direction, and we would call this the reverse direction. But what we do is we look at however it's written, and then we, whatever the left to right direction is the forward direction. So no matter how you wrote it, whether you write it backwards or whether you write it this way, you're still going to say that the left to right direction is the forward direction and right to left is reverse. Does that make sense? I hope. Okay, so this can end up two different ways, really. We saw that with the buckets of water, we saw, a situation where, over time, the reactant concentration comes down, the product concentration rises, but then they level off at some point, right? And again, we said that was because the rate of the forward reaction, this rate here, the rate of the forward reaction becomes the same as the rate of the reverse reaction. So you have the same amount molarity-wise or pressure-wise if you have gases, going backward and forward at the same time, right? And so in this case, you can end up with a case where you have product concentration greater than reactant concentration over time, but again, it's going to remain constant. When you have the same amount of reactant becoming product and product becoming reactant, then the concentrations will remain the same. Another way this can end up is like this. On the right-hand side, you have, where the reactant concentration remains higher than the product concentration when those concentrations level out. So where would equilibrium start in these reactions? It's based somewhere like wherever you think that the concentrations remain constant. So here it's still changing. They're still changing. They're still changing. They're still changing. Looks maybe right about there. And I know I didn't draw that perfectly straight. But right about there, I would say equilibrium happened, yes? So at some point in time, and the time is going to be different for every reaction based on the kinetics, but that time where the two rates become equal, then you are at equilibrium. So Let's look at the definition of chemical equilibrium. Okay, so what is chemical equilibrium? Here's the definition. It is a state of balance, equilibrium, balance, right? Where the rate of the forward reaction of a reversible reaction equals the rate of the reverse reaction in the reversible reaction. And because of that, the concentration, remember the brackets mean concentration, the concentration of reactants and concentration of products remain unchanged. Okay, that's the definition. And here are some important things to remember about chemical equilibrium. First, reversible reactions never stop. They're not like completion reactions. Unless you do something like harvest the product or take the reactant out, it's just going to continue to go, right? Reactant's going to become product, and then some product's going to become reactant, and those concentrations will remain unchanged. All right, it just keeps going. And again, you can do something to stop the reaction, but until you do, it's just going to keep going, because the reactant is not going to run out. And the product's not going to run out. One also thing, a misconception is that the concentrations become equal at equilibrium because the word equa is in there, right? No, it is possible that they may end up equal, but that's extremely rare. Usually you have either the reactant concentration is higher or the reactant concentration is lower, like we saw in the graphs above, right? It can end up usually in two different ways. It usually did not end up with the two concentrations being equal. But many times students believe that that's what equilibrium means, is that the reaction and product concentrations are equal every time. No, nay, nay, nay. What's equal are the reaction rates, forward and back. And that's the third important point. It's also, because the concentrations remain the same, okay, and if you're just looking at the amount of product, okay, like in the bucket of water, the product side of the bucket of water, the height of the water stayed the same over time, right? It was staying the same over time. So you might think that the reaction stopped, right? You might think that it stops, but it doesn't stop. It just keeps going. And so what they say, it is what's called a dynamic equilibrium. In other words, it's always going, even if it looks like it isn't. So we've said that at equilibrium, the rate of the forward and reverse reactions are equal. But when we think about kinetics, aren't somehow the rates tied to the actual concentration at any moment? Right, so there's a tie, a little bit of a tie here between kinetics and equilibrium. Okay, so we're saying that the concentrations, the rates become equal, but the rates depend on the concentrations. Right, and that's one of the factors that affects kinetics. So what we're going to try to do is write what's going on here in terms of the concentrations of reactant and product. So this thing that we're going to talk about in a second is called the equilibrium expression. It's an equation that's going to include the concentrations of reactant and products and try to quantify what's going on at the point at which you reach equilibrium. And it comes from the work of, again, these guys Goldberg and Wavy in the 1860s, and they called it the law of mass action. That's all you really just need. I mean, I think that may be okay to just know that's called that. I don't know if you have to memorize that, but essentially is what is the law? The law of mass action is a mathematical expression that relates concentrations at equilibrium, and they called it the equilibrium expression. It's like an equation. And the calculated value, in other words, if you write the expression and then you measure the concentration of reactant and product, and you plug those concentrations into the equation that you write, and then you solve for the numerical value of that, we call it the equilibrium constant. And guess what? It turns out that at equilibrium, because the reactant concentration and product concentration stay the same, when you do math on them, you have two constant numbers, and it turns out we're going to divide them. But you divide two constants, what do you get? Another constant. And so the value for this thing called the equilibrium constant is constant for a certain chemical reaction, and I'll say this, although we're not going to talk about it today, at a certain temperature. Because of course temperature affects kinetics, kinetics affects rates, rates affects concentration. So ultimately there will be a temperature dependency of the equilibrium constant. It will change its value based on different temperatures, but for a given temperature, for a given chemical reaction, the value of product and reactant concentrations will always be the same ratio at equilibrium, as we're going to see here in a second. All right, so it turns out that basically this KEQ expression, this equation, is the ratio of product and reactant concentrations at equilibrium. Again, if you have gases and you measure their pressures instead of their concentration, it'll be the ratio of product and reactant pressures at equilibrium. Now, what would the law of mass action look like? Okay, so we have nitrogen and oxygen and nitrogen monoxide in this equation. The law of mass action basically says this, and that you take the product concentration or product pressure, we're going to use concentration this time, and so that KEQ can be called a KC, for C for concentration. You take the concentration of the product at equilibrium when, once it's constant, and you raise it to the power of its coefficient. So the numerator, which is going to be the product concentration, it's going to be related to the product concentration, is raised to the power of its coefficient. And this is what Goldberg and Wege found, okay? And if you divide that by the product concentrations raised to the power of their coefficient, did I say product? Reactant concentrations, raised to the power of their coefficient, that's the denominator of the equilibrium constant. So I'm going to take the concentration of nitrogen, and you multiply them, not add them. You don't add them. They're added in the equation, but you multiply them in the equilibrium constant. And these are going to be raised to the first power because that's their coefficient. But because it's the first power, of course, you don't need to write it in. That, my friends, is the equilibrium expression for this reversible reaction. You take the product concentrations in the numerator, raised to the power of their coefficient, divided by the reactant concentrations raised to their power. So here, in other words, you would say KEQ is the mathematical product, by mathematical product I mean times, right, of the product concentrations raised to the power of their coefficient, divided by the mathematical product, the product or dot, of reactant concentrations at equilibrium, but of course they're raised to the power of their coefficient, okay? So it's pretty simple to write the KEQ expression. And now you can see why it's a constant. Because the concentration of NO doesn't change once you've reached equilibrium. And the concentration of N and N2 and O2 don't change. So the value for KEQ will be constant if you measure the equilibrium concentrations and plug them in. And that's what we're going to do in a few minutes here. Give you a scenario and we'll calculate the value of KEQ. So now we're going to write the equilibrium constant in terms of partial pressure. So if you had a container that had water vapor and carbon monoxide, it turns out this is a reversible reaction. It'll create hydrogen and carbon dioxide. And in that vessel, you would have all four species present, right? You'd have your H2O, you'd have your CO, you'd have your H2, and you have your CO2, and they each would have their own partial pressures in this container, yes? If you measured those partial pressures, you can, product and reactant, you can write the equilibrium expression, the KEQ equals, or in this case, you can call it KP, for the equilibrium constant written in terms of pressure, and it would be the pressure of hydrogen gas, the partial at equilibrium, time to the first power, right? These are all coefficients of 1, times the partial pressure of CO2 raised to the first power over the pressure of H2O raised to the first power times the pressure of carbon monoxide raised to the first power. A couple of things. It's important not to write brackets around this. Do not write brackets around the pressure. Brackets mean concentration, and the AP reviewer in May will ding you for it, I've been told. All right. So if you would need to raise it to a power, let's say there was a 2 here in front of the hydrogen, you put parentheses around it and square it. Do not put brackets around it. They don't, because brackets mean one thing, and that's concentration. Okay, but that coefficient really isn't there. So at this point, that would be the value of the equilibrium constant for this reaction at whatever temperature it was run at. Okay. Okay? And so that would be what we would call a Kp, but you can also call it a Keq. It is an equilibrium constant. So think about this. Really, what is it? It's basically the ratio of product to reactant at equilibrium, isn't it? It's a ratio of the amount of product you have divided by the amount of reactant you have, whether you measure it in concentration or whether you measure it in pressure. That's really what it is. And kind of getting to what Matthew asked earlier, what does the value of Keq mean? I'll kind of give it away a little bit now. What if you have a situation where you have more product at equilibrium than reactant? Wouldn't this value be greater than 1? Right? What if it was one of those graphs where you have more product? What if you had twice as much product as reactant at equilibrium? Well, then the value of Keq would be 2 if the coefficients are all 1. Right? And if you have a situation where it's not a very favorable equilibrium to make product, and so the reactant concentration is twice as high than the product concentration at equilibrium, then the value of Keq would be 1/2 or less than 1. So kind of thinking ahead to what we're going to get to is when you calculate the value of Keq, it gives you an idea of, is it an equilibrium where you end up with more product than reactant at equilibrium or more reactant than product at equilibrium? And that's why the value for Keq becomes important. It kind of gives you an idea of how much product are you going to make proportionately to reactant once you reach equilibrium. So it is a hugely important number, okay? But again, we're going to reserve looking more into that, like how high does Keq have to be a good reaction, quote, good? And how low does it have to be a not so good equilibrium, where you don't make a lot of product? All that's to come. Here's another reversible reaction. If you bubble ammonia gas through water, it doesn't just dissolve in the water, it reacts with the water. In fact, this is a Bronsted-Lowry reaction. You may even recognize it. We've done this before. But this reaction includes gases, liquids, and aqueous things. And it turns out what these guys found out, Goldberg and Wege found, was that pure liquids and pure solids don't affect the numerical value of the equilibrium constant. So in a way, and we're going to learn why, but not today, we'll learn why. So solids and liquids don't affect the value of the equilibrium constant, but gaseous substances and aqueous substances do. And so what we can do or will do when we write the equilibrium expression for a reaction that has pure liquids, like here H2O, or pure solids, like we're going to see in the next example, they don't affect the value of Keq, and so you plug them into Keq as the number 1. And again, we're going to learn why this is later, but I'm just going to show you how to do it. So when I write this, I'm going to write Keq, and I'm going to write it as a Kc, a concentration one. So if it's aqueous, and you want to put the whole species in there, so NH4 plus, times to the raised to the first power times the concentration of hydroxide ion at equilibrium raised to the first power. And you would divide that by the concentration of NH3 raised to the first power times 1 in a sense, because this is a pure liquid. And in order for the pure liquid not to affect the value of KEQ, in a sense it has to go in there as 1. Again, we're going to learn why in next class, but not today. All right? So that's it. So the KEQ, in a sense, is what I said before. It's the product of the product concentrations at equilibrium divided by the product of the reactant concentrations at equilibrium. But if the product or reactant is a pure solid or liquid, you would enter that value into the KEQ expression as the number 1. And so then you wouldn't even have to write that number 1 because you're multiplying by 1, and anything multiplied by 1 is it. So this is a little bit more complicated than we said before. Okay, so here's an example again of solubility equilibrium. You have calcium chloride. You put a whole lot of calcium chloride into water and it starts to dissolve. Okay, but you know that the water can only hold so many chloride ions and so many calcium ions. And so at some point, right, you have a saturated solution where calcium chloride, the undissolved calcium chloride, sinks to the bottom of the beaker. But we also learned about, when we talked about solubility, in Unit 4 or whatever, is that this is also dynamic, right? In other words, no more calcium chloride can dissolve, but if one calcium chloride dissolves, then one calcium chloride that was in solution has to undissolve and come back together and make the solid, okay? So now think about this, and how solids don't affect the equilibrium. Right now I'm in equilibrium, right? And I have all this calcium chloride in here. If I dumped more solid calcium chloride, I'm not going to get any more product, am I? Right? So it's kind of a little illustration of how that pure solid isn't affecting this equilibrium. Because I could dump in more calcium chloride, but no more can dissolve. I could have all the solid calcium chloride in the world. But as long as it's only a certain volume of water, I'm not going to get any more solubility, okay? And so that solubility equilibrium is written like this. So what would the value of the equilibrium constant be for this? Well, KEQ. In this case, it's a KC, okay? It's going to be the concentration of calcium ion raised to the first power times the concentration of chloride ion squared over 1, because this is a pure solid, and because it's over 1, then you don't really even have to write the 1. And so if I want to know the value of this equilibrium constant, I would just have to measure the calcium ion concentration and the chloride ion concentration and plug those values in, and I would get the value of the equilibrium constant. Yes?
So that means an equation like this would always favor product formation?
Not always, because you'll see there's a whole 7.11 or whatever is just about solubility equilibrium. We're going to look into it. It could, normally yes, but what if you have something that barely dissolves? Like we said, how sulfides are insoluble. Turns out silver 1 sulfide is the most insoluble compound. The molarity of the silver ions in silver 1 sulfide ends up being something like 1 × 10 to the negative 17th molar. Well, if you have 1 × 10 to the 17th molar concentration at saturation, that's barely dissolved. So you're not going to get a very large equilibrium constant for that one. So it all depends. But for things that we think of as soluble, yes, that will favor the product side. So how do you calculate the value of the KEQ expression? Well, you need to measure those concentrations at equilibrium. So once they become constant, those concentrations remain unchanged, you measure them, or their pressures, and then you plug those molarities or pressures into the KEQ expression. So this is the solubility equilibrium that we just talked about, right? So we know that the first step when you want to calculate the value of KEQ is to write the KEQ expression. So KEQ equals the concentration of calcium ion times the concentration of chloride ion, but you have to square it, okay? And then over 1 because this is a pure solid. Right? Well, then you would plug it in. Well, I measured this concentration, and the concentration of calcium is 0.10 molar times the concentration of chloride. Well, because this is a 1-to-2 ratio, the concentration of chloride is 0.20 molar. Doesn't that make sense? Because you get a 1-to-2 mole ratio, yeah? But you have to square that. And so I think it ends up being 0.004 if you do the math. Yeah? Okay? And so I believe so. Here's the beauty, and we're going to learn again why this is. The units are not molarity cubed. In fact, KEQ is unitless. So all you people out there that don't like to write units, you're going to be so happy. Because no matter what, whether these are pressures in atmospheres or molarities, when you get the numerical value for KEQ, you ignore whatever units were there. There's a reason why, and it's the same reason why solids and liquids don't affect the value of the equilibrium constant, but we're not going to learn about that today. Okay, well, let's look over one more example. So what if I had partial pressures? Okay, well, I'm going to take this, so KEQ, this would be a KP, but you could just say KEQ, is concentration of NO2 squared over the concentration of N2, or not concentration, doggone it, pressure, under pressure, pushing down. Anyway, yeah. So equals, all right, well, pressure of NO2 is 0.17 atmospheres squared over 0.23 atmospheres, and I don't know what numerical value that is. And the numerical value is 0.1256, or again, 2 sig figs is all we have. So 0.13 would be the value of this equilibrium constant. So that's pretty much it. So it's really easy to calculate the value. The important thing to remember, though, is these concentrations you plug in have to be the concentration at equilibrium. All right? And if you want to try and do something with KEQ and you have the initial concentrations and not the equilibrium concentrations, it's still possible to figure it out, but it's a different math, okay? In fact, it's going to be not one of the most difficult things we've done, but it's going to be one that's going to lead us in to be able to handle all the acid-base stuff in Unit 8, and so it's really good. You Science Olympia guys probably know, it's called ice tables. Have you done ice tables? Did you do anything with ice tables? Okay.